Hello, Future Peas. This is Wasim Asgar. I'm a licensed professional engineer in the US and Canada. I've authored several books on the topic of FE Electrical and PE Power, and I run popular exam preparation programs for FE Electrical and PE Power. In this video, you're going to see me taking questions from my PE Power live training students on the topic of motors within National Electric Code or NEC. As you probably know, NEC is one of the heaviest topics on the PE Power exam. It falls under Codes and Standards, section number 1, General Power Engineering. I have a lot of students who come to my program with little to no knowledge of NEC. At the same time, I have students who are enrolled in my PE Power program who are already experts in NEC, and some of them are actually master electricians. The approach that I take to teach my students NEC is based on first principles, and it works out super well for every student regardless of their starting point. NEC is a world in itself. It's a 800 plus page standard. And in the context of the PE Power exam, if you don't approach it properly, then you can be completely lost. After going through my program, even the students who started off with a blank slate when it comes to NEC, they tell me that they start feeling very confident and competent in their knowledge of NEC. Another reason why you should pay special attention to NEC, even outside the context of the PE Power exam, is because it is very practical. If you want to work in utilities, if you want to work as a design engineer or a technical electrical engineer in general within the power systems industry, you have to have at least basic level of understanding of NEC. And if you're new to the US as an internationally trained engineer, or if you're just graduating from school, having a fundamental understanding of NEC can set you apart in the job market. So without further ado, let's dive into the content and learn a few things about NEC specifically in the context of motors, which belongs to Article 430. So this is there was another part. The second part of this question dealt with transformers, which I'm gonna bring up shortly. So this is a deep question, very similar to what you were just alluding to, Jose. Motors. As per NEC 430.52b, for motor branch circuit, and essentially the student copy pasted this particular rule. So from this point onwards, I verified it word to word. It's basically the same. It says for motor branch circuit, short circuit, and ground fault protective devices, motor branch circuit, short circuit, and ground fault protective devices shall be capable of carrying the starting current of the motor. Okay, so that's a requirement. I'll highlight it so that it stands out for you guys. Okay, you guys agree with this? Well, it's in the code. So I mean, whether you agree with this or not, it's irrelevant. It's a code requirement, right? But it makes intuitive sense, right? That the motor, branch circuit, short circuit, and ground fault protective devices shall be capable of carrying the starting current of the motor. Let's challenge it for a second before even moving on to the second part of the real question, right? What if the protective devices are not capable of carrying the starting current of the motor? What is going to happen? Nuisance tripping. Correct, guys? We are going to encounter nuisance tripping. All right? Because whenever the motor starts, you guys remember I explained it in the on-demand. Typically, what is the multiplier on FLC for motor starting current? It's very similar to the transformers. It depends on what type of starting mechanism, obviously, you're using for the motors, right? But let us assume it's direct online. Direct online, DOL, of an induction machine, induction motor. Basically 6 to 8x, correct? 6 to 8x, okay? So that's what the student is thinking. So now in this question, the student is saying that, but in our on-demand, we considered the full load current from table 430.250 of NEC, okay? So we start with the FLC that is provided to us, that is okay, right? Let's treat it that as you're simply running amperage that is offered by the motor to the grid or to the power source, right? And we know table 430.250 very well. You guys can pull it up on the side as well. Are the FLC in the table and starting current the same? So let's address this question right away. FLC and the starting current, are they the same? No. Big no, right? I can just leave this question here and then move on, right? I mean, like, no, they are not the same. So your premise, your basically basis of the question is wrong, right? But this is a deep question. I'd like to explore it with you guys to make sure that you understand where the student is coming from and what we can learn from it. The short answer is that FLC and the starting currents are not the same, right? Starting currents are multiples, right, of your FLC. But that still does not answer this question. That essentially what the student is asking is that how do you make sure that the OCPD ratings and the settings that you come up with using some of the other tables I'm going to mention them, that they are respectful of the motor starting current? How do you approach it, guys? So this is where the code meets the reality. Okay. This is a practical aspect of the code, right? This is not theoretical. In fact, the code is written to address practical scenarios primarily. All right, don't ask me a question over a question, guys. Let's take it one step at a time, okay? So my question for you is, how would you approach it? What are our safeguarding mechanisms? In practice, in reality, how do we make sure that the motors do not trip? Okay, or the OCPDs that are protecting the motors don't undergo nuisance tripping when we are dealing with the starting current. Next size up. Next size up just gives you small margin, right? If you're going from 50 amps to 75 amps, that's what, like 20%, 25%. If you're going from 75 to 100%, that's like 30%, 20%, right? But we are talking about the motor starting current being 6 to 8 times, right? That's 600, 700, 800, 900%, not 20, 30%. Delays, you're onto something on. Jose is saying, I would say testing it and checking if that OCP would be enough. So trial and error? Is that what you're referring to, Jose? That will take a lot of time. It will eventually work, but it will take a lot of time. Is there a more systematic, sophisticated manner in which we can deal with this? There is. And that is called protective device coordination. Agreed? What you're going to do is you will start out with the TCCs, correct, of the motor in question. You will look at the TCCs of the, so the TCC of a motor is basically the motor starting curve, right, for the motor. You're going to look at the TCC for our OCPD. You're going to look at some key milestones. Now, this is the stuff, I know we are still in section number 1, but this is the stuff that I discuss in detail in section number 4. And just to give you a blast from the future, this is how it's going to look like. A typical motor will have the starting curve that is going to look something like this. So the motor is going to have a particular FLA, right? And then you have the motor starting curve, right? This is the lock rotor amps. So we're going to discuss all of this stuff in a lot of detail. So along this curve is where the motor is going to operate, right? Okay. Now, when we select our overcurrent protective device, and this is a question that I ask my students when we get there in section number 4, okay, where should be the TCC of our OCPD be? Okay, and this is the answer. Our OCPD should be to the right of the motor starting curve. Because if it is overlaying the starting curve, right, equipment operating area is to the left of the starting curve, right? It never goes to the right of the starting curve. If we have our TCC of the protected device doing something like this, then it is going to result in the nuisance tripping. Are you guys following me over here? Right? And this black graph that you see is going to prevent motor from getting damaged. Is that clear, guys? Okay. And there's going to be a lot more detail on this when we get to section number 4, when we start discussing TCCs and coordination. Right? Now, is this good enough for us to answer the question that the student is asking? Yes or no? It does. So the way that we address the starting current of the motor is by playing around with the different trip settings of our OCPD. And obviously, which OCPD has trip settings? The breaker or the fuse? Breaker, right? And in the course, I go over in section number 4 in detail about LSIG. So those are the interesting trip settings, right? I've done a lot of these programmings hands-on myself in the field as well, worked with TCCs in SKM, ETAP, easy power, and so on. So you accommodate the motor curve, right? Different points of operation by changing those settings and then making sure that the motor operating region is to the left of your OCPD device as you see over here. Now that still begs a question as to how we pick up the rating, right? The breakers are rated, right? The breakers have certain ratings, fuse have certain ratings, right? And so on. So where does NEC, if everything is done in a TCC, if everything is done on SKM or ETAP, or by looking at these protected devices, are there certain guidelines from NEC? Which rules are going to be applied over here? What do you guys think? Are there any rules that we need to take care of? Obviously, we went through a lot of details, multi-step process, doing the motor calculations, right? In the on-demand course and during the live training. Table 430.52, guys. Maximum rating or setting of the motor branch circuit, short circuit, and ground fault protective devices. So these are the different classes and types of motors, correct? What is the code telling me? The code is telling me that if you want to use inverse time breaker, right, then the maximum rating of that breaker is going to be 250% of what? 250% of the motor FLC. Where do we pick the motor FLCs from? Quickly, this should be fresh in your mind. Which table? Hit me up with the table number, guys. Again, you don't have to memorize it. You'll have the code accessible to you on the exam. But when you're going through the content, and especially using that spreadsheet that I've put together containing all the references, 430.250, right? 430.250 is the go-to table. There are other tables, like I think single phase motors are in a different table, right? 252, I believe, right? But for three phase, this is the go-to table. And most of the motors we encountered, the big motors, are all three phase. There are smaller single phase motors in like small fans and this and that. But yeah, okay. Now, what is this number? 250% of the FLC. So this is where the FLC is coming from. Okay, if you're using a time delay fuse, then the maximum allowance is this. If you're using a non-time delay fuse, then this is this. If you're doing an instantaneous strip breaker, then this is this, right? Now, if I go back to the TCC, guys, you gotta see the interesting thing. What I love about NEC is that if you focus on developing a sound theoretical knowledge, combine it with the practical aspects of things, and try and relate the code requirements, right, as a link between the theory and the practice, it really helps you understand the scenario at hand very, very efficiently, effectively, right? Now, that number that we're looking at, 250% of the FLC, where do you think over here is going to start? Let's focus on this. Actually, let's start from here. I don't know if I actually discussed this in the class. I don't think I remember discussing this, but so the motor FLC is what? This point, you agree, right? They're calling it FLA in ETAP and SKM, right? But that's because it's coming from the nameplate. But for all practical purposes, they're very close to each other, right? So that 125%, 150%, 200%, 250%, whatever the percentages that we were looking at, they are going to be to the right of this blue point or to the left of this blue point. This is the blue point, right? This is the motor FLA, right? To the right, to the right, somewhere over here. This is where it's gonna kick in. Does that make sense? This is where your OCPD is gonna kick in. Whether you have a fuse, whether you have a LSIG, whatever dance that is doing, right? This is where it's gonna kick in. Now let's look at our OCPD. Once it kicks in, guys, over here, this is where it kicks in, right? So if this is my FLA, FLC, okay, let's call it FLC, and this is where my OCPD kicks in, does it ever go to the left? You can make it dance to the right, however way you want to, right? If you're using the LSIG. But that is that trigger. And what the code is in layman terms telling us is that trigger, you have the flexibility, and remember this is the maximum. You have the flexibility, you have our blessing, you have our permission to start that trigger up to 250% of your motor FLC if you want to. Does it make sense? And then once you push it to the right to 250% if you're dealing with the inverse time breaker or instantaneous trip breaker, these are high because instantaneous is boom. There is no LSIG. Instantaneous is as soon as it hits it, it comes crashing down, right? And again, more details in section number 4 about all of this stuff. Okay. Once you actually have that triggered, right, you can accommodate whatever you want to do in this space with your coordination. Clear? So this is a very deep question that the student asked, and I know the student is there. Feel free to, comment on it. But I'm not sure if you were exactly thinking along the same line, pattern. But this is a systematic, step-by-step way of addressing this question, both in practice as well as in an exam-like setting. I think for an exam-like setting, you can create half a dozen questions based on what we've just discussed over here. No exaggeration. Okay, is it clear, guys? So this is the approach that you have to take when you're dealing with NEC. And trust me, if you take this approach with your NEC preparation and by extension with your P-Power preparation, you're going to enjoy these learning sessions a lot. Because then it's not a matter of selecting A, B, C, and D. You're creating a whole framework of understanding that is going to make you a lot more comfortable and a confident engineer. Okay. And to me, more than anything else, that is the biggest takeaway, right? If you can walk away from my program feeling a much more confident engineer, right? To me, that is a greater achievement for me, right? As compared to you just passing the exam barely. Okay. Follow-up question, could you do something similar with transformer? Transformer is the same business. Transformers and motors. By the way, what is a transformer? How can you relate a transformer with an induction machine? You guys remember the statement that I made? Transformer is basically an induction motor with a rotating secondary. It's basically the same thing. All right. So what are the key insights, guys, over here? NEC requirements must be applied in conjunction with practical realities such as TCCs, equipment ratings, and so on. Okay, OEM requirements can ride on top of this as well. OEM is the original equipment manufacturer, right? In practice, we pay special attention to the OEM requirements. For example, if a motor is combined with a VFD, then the VFD manufacturer will have certain requirements. The motor vendor will have some specific requirements, regarding the type of cables that you're using, the distances that you can separate the VFDs from the motor, and whether there's a requirement for a line reactor, a load reactor. They may talk about the SPD requirements, especially for the VFDs. Sometimes they're built in. So this is bare minimum. I want to keep on reminding you again and again. NEC is the bare minimum requirement. There's a lot that goes that you have to do above and beyond in most of the cases. Try to connect the dots from multiple knowledge areas, right? So you can see that I took several steps back in order to answer this question, right? I painted an entire picture. We went back to the TCCs, we went back to ETAP, SKM, coordination, nameplate ratings, key milestones on the TCCs, and that's how we basically answered this question comprehensively, right? So be comfortable in connecting the dots between multiple knowledge areas and learn how to apply multiple code rules to different scenarios. NEC is basically going to force you to do that anyways, right? You cannot walk away from NEC problems by just trying to plug and chug, that I got to look for this particular keyword and this is where I'm going to find my answer. Rarely it happens. To make the overall exam easier, they might do that with some of the problems, right? And they've done that in the NCA sample exam, as you guys can see, right? There's a question in the NCA sample exam about the minimum overall resistance of a grounding rod. Everyone knows that's 25 ohms, correct? So that's a plug and check type of a problem. You don't have to kill your brain cells in order to figure that out, right? But yeah, you have to be comfortable in cross-referencing when it comes to NEC. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE Electrical and PE Power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the PE Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.